As we did in our section on improper integrals, we're going to see how we can develop a test called the comparison test, where we can deduce whether a series converges or diverges by comparing it to a well-known series, something that we already know whether it converges or diverges. And of course the series we know most about are the p-series, which we've just studied, that the sum from 1 to infinity of 1 over n to the p converges for p bigger than 1 and diverges for p less than or equal to 1. And we also know a lot about geometric series. We know that the sum from 1 to infinity of a times r to the n minus 1, where a is a constant, converges if the absolute value of r is less than 1 and diverges if the absolute value of r is greater than or equal to 1. And the comparison test says, suppose I have two series and they both have positive terms. This is very important when you're applying this test. And suppose I know already that the sum of bn is convergent, and I also know that the terms of the series, the sum of an, are all less than or equal to the corresponding terms in the series, the sum of bn. So an is less than or equal to bn for every n. Then I can deduce that the sum of an also converges. And if you think about it, this is fairly obvious from the partial sums. The partial sums of an are always less than or equal to the partial sums of bn, and they're increasing and they're bounded by the sum of the series bn, so therefore that sequence of partial sums for an must converge. Now the second part of the test says that, suppose again I have the two series, the sum of an and the sum of bn, and this time I know that the sum of bn is divergent. And also suppose I know that the terms an of the series, the sum an, are bigger than or equal to the corresponding terms in bn. Then I can conclude that the sum of an diverges. Of course, the reason for this is the limit of the partial sums of the sum of bn must tend to infinity because they're increasing and they cannot be bounded, so they must increase without bound, and also the partial sums of an are bigger than the partial sums of bn, so they must also increase without bound as the size of the sum goes to infinity. Suppose I want to use the comparison test to figure out if the following series converges or diverges. My first task is to find something to compare it to. Now, of course, I must ensure that the terms of the series are positive before I apply this test, and indeed they are. A good candidate to compare this series to is the sum of 1 over n cubed, which is a p-series, and I know it converges. Well, the an's are greater than 0. This is true because 2 to the minus 1 over n cubed is bigger than 0 for n bigger than or equal to 1. And we actually have 2 to the 1 over n is the nth root of 2. That's bigger than 1 for n bigger than or equal to 1. Therefore, 2 to the minus 1 over n is 1 over the nth root of 2, which has to be less than 1 for n bigger than or equal to 1. So therefore 2 to the minus 1 over n cubed is less than 1 over n cubed for n bigger than 1. And now we can compare the series, the sum of 2 to the minus 1 over n cubed, to the series, the sum of 1 over n cubed. The sum of 1 over n cubed is a p-series with p bigger than 1, so we already know it converges. So therefore we can conclude that the sum of 2 to the minus 1 over n cubed is less than or equal to the sum from 1 to infinity of 1 over n cubed, which we know is finite.